Hi, everyone. My name is Grishma Gadikota. I'm a faculty member at Cornell University, and I'm also the founder of Carbon to Stone. And our company got started really to address this challenge here, right? And the challenge that we were really born to address through Carbon to Stone is this challenge of co-utilizing CO2 emissions, as well as vast quantities of alkaline industrial residues. So if you were to look at these figures here, you can see figures of slags, mine tailings, as well as flue gas, right? And there are industries where these residues and these emissions are actually co-produced. And this is really a problem of massive scales. What do I mean by that? About 180 million tons per year of mine tailings are generated, about 360 million tons per year of slag is generated, and just the iron and steel industry alone accounts for 2.6 gigatons of CO2 emissions every year. So what we really need are transformative solutions that can capture, convert, store, use CO2 in an economical manner, but also help them address some of the challenges that they have in terms of disposing these vast quantities of residues that are co-generated. So with that perspective, we looked at what the current state of the art is. So when we look at the current state of the art, CO2 capture technologies exist. Technologies to take CO2 and convert it into a durable solid also exist. But the challenge is that these technologies are very expensive. So conventional technologies for CO2 capture typically involve capturing CO2 from a very dilute source, including air, where we have 420 ppm of CO2, or even flue gas streams that are generated in iron and steel making, for example. And then we take that, we capture that CO2 in a solvent, send it to a regeneration column, right, where high purity CO2 is released, and then the solvent is regenerated, sent back. Then we use that CO2, convert that into a solid. So if you can see this, that's actually a three-step process, and each of these steps occurs at different temperatures. And if you combine these three steps together, the cost is more than $250 per ton of CO2 that's captured. So that's very expensive. It's not very economical. To address that challenge, we developed our own technology, and so our solutions involve developing process-intensified, simpler processes that will capture, convert, store, and turn CO2 into useful end products. So the figure that you see here on the left is one where we can take flue gas streams, and in a single process, we can convert the CO2 into solid carbonates. And our technology, which is patented, involves using regenerable solvents to do that. And this technology actually occurs at temperatures below 75 degrees centigrade, so it doesn't need a lot of heat. It can be easily integrated with waste heat from several resources as well. And then we have another solution that we are developing for direct air capture and conversion of CO2 into useful products. So if we start with flue gas as our input stream, the cost of our process is in the range of $35 to $55 per ton of CO2. If we start directly from air, then our costs are in the range of about $83 to $126 per ton. Our target customers include heavy industry, iron and steel making, mining, and also companies that are seeking to offset their CO2 emissions like Meta, Google, or Amazon. So with this said, the low cost of our technology has attracted a lot of attention, and we also have revenue sources, right? So the end product that we make can sell for anywhere between $14 to $20 per ton of CO2. According to the recent Inflation Reduction Act, we can actually claim tax credits as well. So if you implement direct air capture technologies, we can get about $130 per ton of CO2 that's captured and converted. And then if we do this directly from flue gas, we have benefit of being able to get about $85 per ton of CO2 captured. We also avoid several costs with current state of the art, which include crushing and grinding the rock, tipping fees for actually landfilling these materials, and the costs of acids and bases that are typically consumed in these processes. Our future revenue stream is also looking at extracting metals that are present in iron and steel residues as well as in mine tailings. So those are additional patents that we're in the process of filing right now, which could be added on to this technology if you're looking to increase the revenue source. So with that said, we do have several industry partners. I have to say that our company is really driven by customer need, and we have folks like Nucor, which is one of the leading iron and steel making companies with facilities here in New York State, as well as Novelis, which is one of the fastest growing secondary aluminum manufacturing companies, who are very interested in working with us. So for example, they actually reached out to us and they started supplying vast quantities of materials for our process. They are partners with us on carbon removal efforts, and we are in the process, as you're speaking, developing pilot scale facilities in collaboration with them. In terms of our development scale, we incorporated this summer, and we're in the process of raising non-dilutive capital. We've actually put in a proposal with Frontiers, which is a carbon marketplace. So we are the suppliers of the carbon credits and they're buyers of the carbon credits, including companies like Google and Meta. So those are aspects that we're working on right now. And very soon we'll be looking to launch a seed round, if you would, over the course of within the next year or so. Our technology is proven at the bench scale, but the next step is to actually take it and prove it at the representative conditions within the industry scale. So that's where we'll be looking for pre-pilot and pilot scale studies, and we'll be needing some Series A funding and so on. And then over the course of the next 5 years, we're actually looking to go to sales with a fully scaled up facility in collaboration with our industry partners. So with that, I really would like to acknowledge my very talented team. So I'm one of the founders, and I'm the inventor of this technology, but really all these industry collaborations would not come about without the support of Shravant Garikota. He has an MBA, a lot of experience in molecule to market translation of technologies, as well as Hasnain Asghar and Suhaib Mohammed, who are PhDs from Cornell, who have extensive experience in carbon capture conversion technologies as well, and are heavily involved in this effort. Also like to acknowledge support from Praxis Center for really giving us inspiration to get us started on our journey towards commercialization. In terms of acknowledgements, really, the reason why I'm standing here is because we've had very generous support for my research group to help actually patent these technologies. And a lot of the support came from grants from DOE, NSF, RPE, to the order of more than $5 million. And that has really helped us create the foundation of patents, as well as helped us de-risk the technology and engage in customer discovery. So I could be standing here and talking to you about what it is that we are looking to do in terms of translating our vision into the commercial landscape. So with that said, thank you everybody for your time.
So in terms of when you work on getting the technology to a commercial scale, what does it look like past the initial development stage where we raise a few $1 million? How capital intensive is this? Do I need a big factory to build this stuff? Do I bring it to my customers to do it on site where their slag is? What sort of money do I have to write a check for you?
That is a great question. So we are looking at effectively two ways to bring our technology to market. So for companies that are looking for more modularized systems, we can actually develop the system for them. We can analyze the waste stream that they'd like to use for offsetting the CO2 emissions, and then we can actually deliver that technology to them. But then for companies that are looking for much larger level of engagement, they actually want to co-develop a technology with us, then we can actually step in as a partner and help them perhaps even license some of our technology. So we're looking at these two different models, one where we develop the reactor system, the equipment, the know-how, and provide this as a packaged service to them. And another where if they want to work with us on a much more extensive level and want to co-partner with us, we'll look at licensing our technology to them as well. We'll have to work out what those terms look like.
Judges, anything else?
What is your competition? I'm sure there are other people like yourself out there looking to improve the technologies. Are you coordinating with any other campuses or other people in your field? Where is what's the future of this?
That's a great question. So the current state of knowledge and the current art, if you will, in this space is what I showed earlier with the conventional carbon capture mineralization, where people have to have multiple unit operations and many, many processes first to capture the CO2 and then mineralize the CO2. They don't have an intensified, integrated process that will do everything in a single step, which is the invention from our group. And also for that reason, our process is much more economical. But then you might ask, what is the catch? Right? So the catch is that we use a regenerable solvent. And what that solvent does, it captures the CO2 and supplies the CO2 for mineralization. And our overall economics are really dependent on how effectively we can regenerate that solvent. So that's a risk factor that we are actually working on very actively in my group. So for every cycle, we're able to regenerate more than 95%. And that actually helps us reach our carbon negative goals. So in many ways, this is a technology to deliver carbon negative solutions. And it's very closely tied to the process optimization goals that we're working towards at this point in time.
Excellent. Thank you so much.